So far, you've learned how functions take an input and give an output. But what if we want to reverse the process? Can we go from output back to input? This is where the concept of invertibility comes in. A function is called invertible if there exists another function that can reverse its effect. That is, it brings the output back to the original input. Think of it like decoding a message or converting Fahrenheit back to Celsius after conversion. Let's define it formally. Suppose there is a function f from set x to set y. That means f is a function from x to y. Now, f is called invertible. First condition, if there exists another function, say g, from y back to x. This means g composed with f equals the identity function on x. Second condition, f composed with g equals the identity function on y. If both conditions are true, then g is called the inverse of f, and we write it as f inverse of x. Let's take an example to understand invertibility in action. Let the function f be defined from the natural numbers to a set y as f of x equals 4x plus 3. Then the range y is defined as y in natural numbers such that y equals 4x plus 3 for some x in natural numbers. Now, let's define another function g from y to natural numbers as g of y equals y minus 3 divided by 4. To check if f is invertible, we verify two conditions. First, g of f of x equals 4x plus 3 minus 3 divided by 4, which equals x. Second, 4 times y minus 3 divided by 4 plus 3, which simplifies to f of g of y equals y minus 3 plus 3, which equals y. Since both conditions hold true, f is invertible. To undo what f did, we subtract 3 from y, then divide the result by 4. That's how you verify invertibility step by step. When is a function invertible? Here's a powerful rule to remember. A function is invertible if and only if it is both one-to-one and onto. Let's break that down. One-to-one means that different inputs produce different outputs. No duplicates, so we can trace back each output to a unique input. Onto means that every element in the code domain is covered. There's no output left out, nothing is missing. But if a function is not one-to-one, multiple inputs might lead to the same output, and that means we can't reverse it uniquely. If it's not onto, some outputs have no preimage at all. So again, reversal is not possible. So remember, invertibility equals to one-to-one plus onto. Only then can a function have a well-defined inverse. Here's a checkpoint for you. Let's take the function f of x equals to times x, defined from natural numbers to natural numbers. Now let's test for invertibility. Is it one-to-one? Yes. Each input gives a unique even number, no repeats. So, the function is one-to-one. Is it onto? No. Because some numbers like 1, 3, 5 are odd, and they'll never be reached by multiplying by 2. So the function misses parts of the codomain. That means it is not onto. Since f is not both one-to-one and onto, f is not invertible. Here's a useful trick when dealing with finite sets. Suppose we have f is a function from set x back to set x, and the set x has a finite number of elements. Then something interesting happens. If f is one-to-one, it's automatically onto. And if f is onto, it must also be one-to-one. So, in finite sets, either property alone is enough to guarantee that f is invertible. But be careful, this trick doesn't work for infinite sets, like the natural numbers or real numbers. In those cases, you have to check both properties separately.
Visually, we can test if a function is invertible using something called the horizontal line test. Here's how it works. Draw horizontal lines across the graph of the function. Now observe. If any horizontal line intersects the graph more than once, the function is not one-to-one, and that means it's not invertible. Let's look at two examples. First, the graph of y equals to x cubed. Every horizontal line intersects it only once. That tells us the function is one-to-one and invertible. Now take y equals to x squared. Many horizontal lines intersect it twice. That means the function is not one-to-one, so it's not invertible over all real numbers r. So remember, one hit per line, invertible. More than one, not invertible. That's the power of the horizontal line test. Let's summarize what we've learned so far about invertible functions. A function f is invertible if there exists another function called f inverse such that f inverse of f of x equals x and f of f inverse of y equals y. This means applying the function and then its inverse brings you back to where you started and vice versa. But for a function to be invertible, two key conditions must be met. It must be one-to-one. Every input gives a unique output. It must be onto every output in the codomain must be used. You can use substitution to verify these conditions in real problems. Why does this matter? Because invertibility is essential for solving equations, reversing processes, and understanding transformations in higher mathematics.